Hello, and welcome to another lesson from Level Up Mathematics. In today's lesson, we will be exploring the transformation of rational functions. Before we do, let's look at some rational function basics. Rational functions have the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions, and q of x cannot equal 0. Rational functions may have vertical and or horizontal asymptotes. An asymptote is a line that a graph approaches but does not reach. Vertical asymptotes occur where the denominator would equal 0. And each piece of a rational function is called a branch. So if you look at this rational function shown to the right, I want you to notice that we have two branches, one on the right side and one on the left side. Those are our two branches of this function. Now, let me erase that shading here. These branches approach a vertical line, but they do not cross it. And that vertical line is not a part of the graph. So I'm going to sketch in this vertical line with a dashed line to indicate it's not part of the graph, but you can see it here. Now, that is called my vertical asymptote. And in the example, it says identify the asymptotes of the rational function shown on the right. So our vertical asymptote would be the line x is equal to positive 2. That's the imaginary line that those two branches approached. Now, our graph also has a horizontal asymptote. I want you to study the graph and see if you can figure out where the horizontal line is that both branches approach, but they never cross. All right, welcome back. Hopefully you can see that both branches approach this horizontal line. So our horizontal asymptote would be y equals -1. Now, before we get started in the transformations, I want to look at the most basic rational function we have, which is the parent function. Now, sometimes we call this the reciprocal function, and the equation for this parent function is f of x equals 1 over x. So the graph is shown below, and what they want us to do is create a table and then identify the critical attributes. So what I'm going to do is I'm going to make a table, 1 over x. I want to make a table on my calculator here. And let's see, table. So I need a -3. And so it's negative, we'll fill in this table here, -0.3. So you can see on this graph, if I go to the left 3, 1, 2, 3, and down 0.3, I would land right here. All right, for -2, it says my value is -0.5. So let's plot that point, -2 and -0.5. Then for -1, we have a point at -1, -1, -1 right here. Then for 0, it's undefined. Now let's talk about why is it undefined at 0? Well, if this denominator were to equal to 0, the graph would be undefined. So that's why the graph will split and make two branches. So for 0, I'm going to put undefined. When x equals 1, we have a value of 1. So that would be right there. When x equals 2, we have a value of 0.5. And when x equals 3, we have a value of 0.3. So let's graph those. 1, 2, 0.5, 3, 0.3. So there's our branches. Now, our vertical asymptote here. So look at the graph carefully. Both branches approach a vertical line, but never cross it. So let's draw that vertical line in. So it approaches this vertical line here. And so the equation of that vertical line would be x equals 0. All right, both branches also approach a horizontal line, but do not cross it. That would be right here at y equals 0. So for our domain, the domain would be the set of all x's such that x cannot equal 0. For the range, the set of all y's such that y cannot equal 0. All right, now the transformations of the reciprocal function are the same as the transformations of any function you've studied thus far in the course. All right, so here is our transformed version of the parent function. It would be f of x equals a over x minus c plus d. So if we change the parameters of a, c, and d, we can move this function around on the grid. So let's talk about what c does first. You probably already know this, but when c is positive, the graph will shift to the left. When it's minus, it will shift to the right. Now, if you look on the right side here, I have my Desmos opened and I've made some sliders so you can see. So let's talk about positive. So right now it says that c equals 0, but if I move my slider and make c equals 1, do you see how it moved to the right? 2, 3, 4, 5, and so on. All right, let's go back to 0. What if I make my c minus or negative? 1, dun, dun, dun. Do you see how it moves to the left? Okay. Now, let's look at some vertical shifts. So D is the vertical shift. A plus would move the graph up, and a minus would shift the graph down. So let's explore that on the slider. So I will explore if D is bigger than 0. So notice how the branches are moving up. Now let's go back to 0. Let's look at what happens when they're negative. The graph simply shifts down. The shape remains the same. All right, so let's go back to 0. Okay. Now, if A is negative, let's look what happens. So I'm going to go here to A. Right now I have A equal positive 1. I'm going to change it to a negative 1. Watch what happens again very closely. Here's A equals positive 1. A is positive 1 here. Let's change it. Notice where the branches are. They're in quadrants 1 and 3. Now let's change it to negative 1 and watch what happens. Now the branches are in quadrants 2 and 4. So we say that if A is negative, the function is reflected across the x-axis. Go back to A equals positive 1. All right. Now, if the absolute value of A is bigger than 1, this will represent a vertical stretch. So let's say that A was positive 3. 1, 2, 3. So when A equals 1, in the original, let's say we have a critical point at 1, 1 on our parent function. Let's say I made the stretch, let's say I made the A value 3, 2, 3. Now, notice now that that point becomes not 1, 1, but 1, 3. It's a vertical stretch of the Y values, okay? Now, if the A value is between 0 and 1, we would have a vertical compression. So let's say we had a vertical compression of 1/2. 1, 1 would become 1, 1/2. Right? The Y values would compress. Okay. Now, our vertical asymptote is determined by the value of c, so it's x equals c. The horizontal asymptote is determined by the value of d, so it'd be y equals d. And all this will make a lot more sense when we actually do some examples here, all right? So in example 2, it says graph each function and identify the domain, range, and the asymptotes. So in problem A, we have f of x equals x plus 3 minus 2. So if we look at our value of c, we have x plus 3. That means this graph will go left 3. And then we have a d value of negative 2. So that means our graph will move down. So left 3 and down 2. So our vertical asymptote will be x equals negative 3. And our horizontal asymptote will be y equals negative 2. Now I'm going to plot those asymptotes for you. So x equals negative 3 would be like right here. And our horizontal asymptote of y equals negative 2 would be right here. So this is like your new 0, 0 right there, okay? Now, when I graph these, remember our parent function had critical values at negative 1, and positive 1, 1, 1. I'm going to still plot those critical values, but just from this new 0, 0 right here. So if I plot negative 1, negative 1, let me get a different color here. From this new 0, 0, I'm going to go left 1, down 1. Okay, so my branch here it's going to curve and it's going to approach these asymptotes. So it's going to approach this asymptote on this side, and it'll approach the horizontal asymptote on that side. All right. Now go back to that new 0, 0. Now I'm going to put a critical point from the new 0, 0, go right 1, up 1. So that's the turning point here of my branch. So it's going to approach the horizontal asymptote like this, and it'll approach the vertical asymptote. Oh, I didn't want a straight line. Where's that? Let's see. It's more of a curve, so it's going to look something like that. All right. Now, the domain and range are going to come from your asymptote. So the domain is the set of all x's such that x cannot equal negative 3, because that's where your asymptote is. And the range, y, is the set of all y's such that y cannot equal negative 2. So the domain and range are always going to come from your asymptotes. That's why it's so important to get your asymptotes first. All right, let's look at another example. We have f of x equals 1 over x minus 1 plus 3. So this graph is going to move right 1 and up 3. That means our vertical asymptote will be at x equals positive 1. So let me draw that in. And our horizontal asymptote will be y equals positive 3. Let me draw that in. 1, 2, 3. Okay. Now, this creates a new 0, 0 right here. That's our new 0, 0, okay? So, from our new 0, 0, I'm going to use these critical points, negative 1, and positive 1, positive 1. So from that new 0, 0, I'll go left 1, down 1, and that's where my new branch is going to curve. So when I curve it, it'll curve towards this vertical line on the right and this horizontal line on the top. Now I'm going to get my other branch. So go back to my new 0, 0 and go right 1, up 1. That's where that branch is going to curve. So it's going to look like that. Okay. Now, I want you to notice that when I graph this on my calculator, let's see, you will not 1 over x minus 1 side arrow plus 3. Notice that when you graph it on your calculator, the asymptotes are not drawn in. That's because they're imaginary lines that the graph approaches. They're only an aid to help you create the graph. They're not part of the final graph of the function. Okay, they're just there to help you sketch the function. All right. Now, lastly, I want to get my domain and range. So the domain would be the set of all x's such that x cannot equal positive 1. The range, the set of all y's such that y cannot equal positive 3. All right. Problem C, f of x equals 2 over x plus 1. Now, this is the first time we've had something besides a 1 in our numerator. So I know this is going to be a vertical stretch by a factor of BFO 2. A vertical stretch by a factor of 2. I also know it's going to go left 1. Left 1. Now, we could also, to make this a little easier, you might want to put a plus 0 out to the side. A plus 0. Okay? So 2 over x plus 1 plus 0. So my vertical asymptote is going to be x equals negative 1. My horizontal asymptote is going to be y equals 0 because that's the value of d. All right, so let's draw these asymptotes in here. Our vertical asymptote at x equals negative 1. Our horizontal asymptote of y equals 0. So our new 0, 0 is going to be right here, okay? Now, we have to be careful on our new 0, 0 because in our original parent function, we had these critical points where the graph turned, negative 1, negative 1. But in this case, we have a vertical stretch by a factor of 2. So this will become 1, comma 2. This will become negative 1, negative 2. So when you're plotting this, go back to your new 0, 0 and go over 1, up 2. That's where your right branch will curve. So it's going to curve towards the horizontal asymptote on that side and towards the vertical asymptote on this side. Okay. Now your left branch, go to your new 0, 0, this green dot, and go left 1, down 2 because it was stretched. And it'll curve towards the vertical asymptote on the right, and it'll curve towards the horizontal asymptote on the left. All right, so for our domain, the set of all x's such that x cannot equal negative 1. For the range, the set of all y's such that y cannot equal 0. All right, problem D. We've got a lot going on problem D. Let's start with that negative 4 in the numerator. That means there's going to be a reflection across the x-axis. It's going to be vertically stretched by a factor of, or BFO, 4. It's going to move right 2 and down 1. Now your asymptotes, for your asymptotes, that's the only two things you need to know to get the asymptotes. We'll deal with the reflection and the stretch in just a minute. Okay, so for my asymptote, I'm going to know that x is equal to 2. That will be my vertical asymptote. And my horizontal asymptote, y equals negative 1. So this will be my new horizontal asymptote. So my new 0, 0 is right here. Okay. Now, if I'm going to reflect across the x-axis and I'm going to stretch by a factor of 4, that means 1, 1 would become 1. If I multiply the y value by negative 4, negative 4. So let's go to my new 0, 0. and go right 1 and down 4. 1, 2, 3, 4. So that means this branch is going to curve around like that. Okay. Now my other critical point, -1, -1, same thing. I've got to stretch that y value by a factor of -4. So this would become -1, and -1 times -4 would be +4. So for my new 0, 0, go left 1 and up 4. 1, 2, 3, 4. So that's where the branch is going to curve. So it'll go curve this way and then this way. So for the domain, the set of all x's such that x cannot equal 2. For the range, the set of all y's such that y cannot equal -1. All right, in our last example, let's practice writing equations for reciprocal functions given the required information. So in problem A, it says the reciprocal parent function is translated 3 units left and 4 units down. Then it's reflected across the x-axis. Write an equation to represent this new function and identify the asymptotes. So remember, our basic equation is f of x equals a over x minus c and out to the side plus d. So in this problem, our function is reflected. So that means our a value is going to be -1. So f of x equals -1 will be the numerator. Okay. Now, it's also translated 3 units to the left. So the denominator would have to be x plus 3 to make it go 3 to the left. And then it moves 4 units down, so the value of d would be -4. Okay. So our vertical asymptote, x equals -3, horizontal, y equals -4. All right, in problem B, the reciprocal parent function is translated, let me highlight this, 5 units up, 2 units right, and vertically stretch by a factor of 3. Write an equation to represent the new function and identify the asymptotes. So for my new function, f of x would equal, I'm vertically stretched by a factor of 3, so that is my numerator. I'm going 2 units to the right, so x minus 2 is my denominator. I'm also translating up 5, so out to the side, plus 5. So our vertical asymptote would be x equals +2. Our horizontal asymptote, y equals 5. The 3, the numerator, does not affect your asymptotes at all. Okay. Problem C. A reciprocal function has a vertical asymptote at x equals -5 and a horizontal asymptote at y equals -4. Write an equation that could represent this function and state the domain and range. So in this problem, it doesn't tell us if it's been reflected or stretched. So we're going to assume that the numerator is 1. Okay. It tells us we have a vertical asymptote at x equals -5. So that means the graph has shifted to the left 5. So that would be x plus 5. We have a horizontal asymptote at y equals -4. So that tells me the graph has been shifted down 4. Now, then they want us to state the domain and range. So I need to mark this out. This should have been domain. Would be the set of all x's such that x cannot equal -5, and the range would be the set of all y's such that y cannot equal -4. And that concludes today's lesson, Transformations of the Rational Parent Function.